Welcome to my Physics 2212 Lab 2. Introduction. So the purpose of this lab was to prepare charged tape and observe their interactions with each other, then experimentally find the charge that a piece of tape holds by using a computational model that creates a string of point charges and calculates the net electric field. Then compare the computational results to the previous experimental results, which created the tapes as point charges, or treated the tapes as point charges. The fundamental principles would be Newton's second law, F equals ma, force due to gravity, F equals mg, and Coulomb's law. The result of this lab was that the magnitude of charge on one piece of tape was 2.945 e to the negative 8 coulombs, which was about 2.25 times bigger than our last results. So main physics ideas and models, F equals ma. In this case, acceleration would be gravitational acceleration. Also, Coulomb's law. This is important because it can determine like the magnitude of the force. So you see it's inversely proportional to the square of the distances in between the charges. So basically, the bigger the distance is, the weaker the force is going to be. Also, opposite charges will attract each other, and like charges will repel each other. And this can help us determine the sign of one charge if we know the sign of the other. And also, here's our experimental model where we set up a piece of charged tape on two ends and brought another piece of charged tape next to it. So in our previous experiment, we charged a piece of tape by ripping it off another piece of tape, and we found that the tape held a charge of 1.3 e to the negative 8 coulombs. And we saw that the tape was attracted to a negatively charged pen, but repelled by another piece of charged tape, which means that the charged tape must have been positively charged. Reasonings, so from Newton's second law, no acceleration equals the net force of zero. So this means the force from gravity and electrostatic force should cancel out. So using this assumption, we can find out the charge, the magnitude of forces, and the number of electrons. The system in this case would be the top tape. The surroundings are the universe and the bottom tape. Initial conditions where the top tape is at rest with only gravity acting at it. And we're also going to assume that each U-tape we made had about the same amount of charge and was evenly distributed along the length of the tape. Also that the two tapes are identical in size and mass and should have the same exact charge when we perform the charging process. And lastly, we're going to assume that the charges are evenly distributed across the surface of the tape. So for our calculations, Fe equals Fg, because they should cancel out. Here we calculate mg, and this is our formula for Fe, where we treat it as a line of charges, where S is the distance between the two tapes, L is the length of a tape, and here we solve for Q by setting this equation equal to Fg, and this is what we get for our charge. The computational model was scripted to calculate the net electric field along a chain of identically charged particles, and it used the experimentally found charge of the tape and used that as a charge for one of the infinite particles in that chain. Then used every charge on the bottom chain to calculate the total electric field and sum them to find the net electric field. Then it generated a visual of the tape chains with the force due to the gravity and the net electric force acting on the top tape from the bottom charge. Here we can look at our code. Here we plug in our constants. Here we make the electric field. Here we define the line charge. And here we're creating the top tape and the bottom tape. Here we're finding the net electric force on the top tape. We're finding dq on top tape and dq on the bottom tape. And then we calculate the net electric field and the electric force. And here we're like visualizing it. So for our results, here's our visual, and this was the magnitude of the electric force, this was the magnitude of the gravitational force, and we see that the magnitude of charge on one piece of tape was about doubled. So the previous experiment compared to the new computational model, the previous results were smaller. The original experiment showed a charge of 1.3 e to the negative 8 coulombs, which is about 2.25 times smaller than this computational model. And sources of error could be that our measurement of the tape length was inaccurate, and this would impact the calculated mass and area. Also, it could have been difficult to measure the distance that the tape rose up, which would affect our formula for electrostatic force. And lastly, the charges could have not been evenly distributed across the tape. Conclusions. So what if you modeled your tapes as a single point charge? If we did a point charge, it would have been 1.3 e to the negative 8 coulombs versus the charge chain model we did this time, which was 2.945 e to the negative 8 coulombs. And why do these estimates differ? These estimates differ because in this computational model, each point charge is being calculated against one another, so every individual interaction is measured. Thus, the estimate with the chain charges is probably more accurate and closer to the real value because it accounts for interactions the point charge does not. Thank you.